Welcome to our video lesson for section 1.3, Graphs of Equations. We're going to be looking at different functions and analyzing their behaviors, discussing their domain and range values, and also looking at different features. Let's get started. We're going to start by reviewing domain and range. So if we look at a graph, we can figure out our domain and range. Basically, for our domain, just to review, it's what's happening from left to right. So another way to consider that is what are the possible x values? That's what we want to know. So we have x values. And then if we look at our range is what happens as we go up and down. So instead of x values, we're going to call that our y values. So what we're trying to figure out is, does the graph stop? Does it turn? Does it have any kind of behavior that would restrict our x or y values? And then once you know what that is, we can write down the actual possible x, y values, which will describe our domain and range. Let's look at a couple examples. All right, so our first example, we have the equation of y equals 1 over 3x squared minus 1. And what you might not be able to see is we do have some invisible lines here that are our asymptotes. And those are some restrictions on our function in terms of the behavior. And we notice that the graph turns at those values. So I'm going to draw in some lines here. These lines are going to represent, again, our asymptotes where the graph does not exist because we can't cross over asymptotes except for a couple special occasions. So when we look at our graph, if I'm going from left to right, I see that I have this left portion, there's a gap, I have this middle portion, another gap, and then I have this right portion. So if I'm talking about my domain values, again, as we go from left to right, I'm missing these two very important pieces. I'm going to go ahead and let you know what those are. So we have negative 1/3 and we have positive 1/3 as our values. That's what's missing. So for my domain, it would be everything except for those two numbers. If I consider my range, so my y values, I can see that my left portion is kind of going up. Again, we have my middle portion, and then I have my right portion. But I'm missing a very specific kind of gap here in the middle. And I can kind of draw these lines. So I'm missing some specific y values there. And for our values, it's basically from about 0 to right up to -1, but not including -1. So when I'm talking about my range, I have all my values except for the values between 0 and -1. So our next step then is, how do we go ahead and write this down? What's the notation look like to signify the correct domain and range? All right, let's go ahead and discuss our domain. So if you look at our left piece over here, it starts off at -infinity and keeps going all the way up until we get to a -1/3. So we're going to include that for our first portion. We have -infinity all the way up to -1/3. For my middle portion, we're going to be going between -1/3 and positive 1/3. And then for my right portion, we start at 1/3 and then go all the way out to infinity. For every one of my values, I'm using parentheses because we don't actually touch at those values. We have our asymptotes, and then we never can actually touch infinities either, so they have parentheses. For my range, we're going to be going from bottom to top. So for my bottom, I'm going from -infinity all the way up to -1. And then here I start at 0 and I go all the way up to positive infinity. So I'm going to represent those. Again, we have -infinity all the way up to -1. And we do actually touch at -1, so we're going to have a bracket there. And then we go from 0 up to infinity. And now we have identified our domain or range, again, using our brackets. All right, the next feature we're going to be talking about is the increasing versus decreasing feature. So we got some fancy notation here. Increasing is, a function is increasing if for any two values, x1 and x2, x1 is less than x2, which implies f of x1 is less than f of x2. All right, so basically what this means is the graph slopes up. That's what all that fancy notation is. So if we have two different x values and the y values are increasing, then our graph is increasing. So if we want to look at our graph and kind of identify some areas where this is happening, well, we're increasing from right around here to about there. And again, I know I'm increasing because if I trace the graph for that portion, we're actually going up. And then my second portion where I'm increasing is going to be from here. And it never stops, right? It just kind of keeps going. So what I'm going to do now is approximate those values. And I'm going to use this for using interval notation again. So let's see, we have probably about -2.1, something around there. And we're going to be increasing all the way up to I'm going to say about 0.9. One of the most important things here to reiterate is for our increasing intervals, we're looking at the x values where the graph is increasing. So for my first portion from here to there, these are the corresponding x values, not the y values. And then for my second portion where I'm increasing, it's going to start right around 4, and it just keeps going. It never stops increasing for this portion. So I have two separate areas of the graph where it's increasing, and I've noted those intervals where it's increasing as well. All right, looking for decreasing values, a function is decreasing if for any two x values, x1 and x2, x1 is actually greater than x2, which implies that f of x1 is also greater than f of x2. So for two x values, if the y values are going down, the graph slopes down and it's decreasing, the opposite of what we had before. So we're looking for two areas where basically we have a negative slope. All right, so our first negative slope is going to be this area here. And then our second negative slope is going to be right around here. Now, one thing that sometimes happens, but not always, is our values here are the same as for our increasing values for part of our intervals. Notice we have the left side of two portions. We have, again, this was one of our intervals here increasing, so we have the left side of that, which means this number should be the same. Same thing over here for our decreasing value. It goes up to one of the values we use for our increasing, so it should be the same that we used, just to kind of be consistent. So for our first decreasing portion, we're going from x equals negative infinity all the way up to negative 2.1, again being consistent and using the value I used for my increasing intervals. And then for my second decreasing portion, I said it's going to be from 4. Oops, that's actually the endpoint. Let me fix that real fast. It stops at 4. It starts at about 0.9. Oh, I should use a bracket there too. All right, let's get this right. About 0.9 all the way to about 4. And again, I use brackets for both of those because we're touching at those versus not touching. All right, if our graph isn't increasing or decreasing, then it's got to be constant. And what that basically means is what we can see here is the y values are the same, and visually what we see is a horizontal line. So if something is increasing, if it has a positive slope, it's decreasing with a negative slope, it's horizontal. If the y values are the same, meaning that we have a horizontal line. All right, so we have a graph here. It might be a little hard to see, but it's the blue portion. So we have this portion, then we've got a curve, and then we have another flat portion. We want to identify the intervals where the graph is increasing, where it's decreasing, and where it's constant. Okay, so for increasing, we're going to go with blue. For decreasing, we'll go with red. And then for constant, we're just going to go with green here. All right, so our increasing portions, well, I know it's going to increase when it's going up, and it's going to be going up from around here to around there. All right, so we're going to go ahead and visually approximate those numbers. I'm going to say that it's starting at about negative 1.5, and it's going to keep increasing until about positive 1.5. And again, we don't have to be that specific. We're just trying to be as approximate as we visually can because we have no other aids here. Okay, so that's my increasing portion. For decreasing, well, we have two decreasing portions. And again, notice how my values are kind of overlapping here, so I can be consistent with that. So it's going to decrease from negative 3 to negative 1.5. It's also going to decrease from about 1.5 to positive 3. And to finish it out, we have our constant areas, which we have over on the left and on the right. And I'll write this up on the top here. So we're going to go from negative infinity to negative 3. And then for our second constant, we're going from, oh, that should be a bracket. We are going from positive 3 to positive infinity. Again, our infinity values always have parentheses because you can never actually reach them, but the rest of our values are all brackets here. All right, guys, your turn here. I would like for you to just identify the correct increasing intervals. That's all we're going to focus on for this example. So you're going to see a question here. I'll have a multiple choice option. Select the correct one, and we'll see if you're correct. Okay, so we're increasing in two specific areas, starting here at about negative 0.8, and we're going to keep going until we stop about at 1.8. That is our first increasing portion. And then our other section at the very top is always increasing. So we're increasing for the rest of the graph starting there, which is pretty much at 3, all the way to infinity. So those are our two increasing intervals. All right, relative minimum. So there exists a relative minimum on a graph if for x1 and x2 there is some value between them. And what this really means is we have a valley. So I'm looking at two very specific portions on our graph here where I can see that we have a valley. We have one here and one here. And as we trace the function, we can see, so it's going down, it stops, and it goes back up. So that point where it stops is my valley, and that's my relative minimum. And all that means is it's the lowest point on a specific area of the graph, meaning we have our valley there. And then over on the right, again, we can see it's going down, it stops, and it goes back up. So that stopping point are going to represent our minimums. And we again need to identify our x values. We're going to approximate those. For the first one, I'm going to say it's pretty much about negative 2.1, something around there. And then for our next one, it looks really, really close to be at exactly 4. So those x values are going to represent where our relative minimum exists. For relative maximum, we have the opposite. So we have some value between our two x's where our y values are increasing. And we have one peak, which is what I'm going to call them. So values are minimums, peaks are going to be maximums. And we just have to approximate that. Just to verify it is a peak, we can see the graph is going up, stops, and goes back down. That stopping point, again, is our peak, which represents our relative maximum because it's the highest portion in that area. I'm going to go ahead and approximate that to be at about 0.9. And since you're just kind of visually approximating, guys, if you're a little off, it's okay. I want to make sure that we are close there. We're going to have some tools using our scientific calculators to get more specific and more accurate with these things. But for right now, we're visually doing it, so we're doing the best that we can. All right, for our line here, we can see that it's continually increasing. So if I'm asking for relative minimums or maximums, it has none. Because as we can see, there's no peaks or valleys, right? I'm going up, I'm going up, I'm still going up. There's no point where the graph turns to go back down and then back up again. So we don't have a point where we have a peak or a valley, meaning that we have no relative minimums or maximums. This would also be true if we had a horizontal line or a vertical line. There would again be no relative minimums or maximums. All right, so we don't have any values on our axis here, but we can identify how many of each that we have. So if my question was how many relative minimums or maximums we have, we could identify that answer. So for the relative minimums, again, we're looking for valleys. How many times do we have a valley? We actually have one. So there's one relative minimum. And if I'm instead looking for relative maximums, I can see how many peaks I have. And we can see there are two peaks. So we have two different relative maximums. So while we can't identify the x values for these, we can at least identify how many of them we have. All right, for our next behavior here, we're looking at even functions. So an even function is symmetric to the y-axis. And what that means is the y-axis acts as its axis of symmetry. So if I had my graph and I lined it up on my y-axis and I folded it over the y-axis, it would fold right on top of itself. And then we have an algebraic approach as well. For every x in the domain, we can see that f of negative x is the same as f of x. And what that really means is if you have a point xy, you have the exact same point, negative xy. One really clear example of this is a parabola. So if I were to draw a parabola on my graph, I have a point, and say that I have this point over here, which is negative 1, 3. In order for this to be an even function, that means that I have to have the point positive 1, 3. So my x values are exact opposites, my y values are exactly the same. And we can algebraically prove this by plugging in negative x and getting the exact same function, which we will try a little later in our notes. So here we can again see three different functions that are even, an extension of our parabolas. For our red function, it's a little bit wider, but if I were to find a point, which I can find some specific points here, let's say I have this point here, which is about negative 3 and almost at about positive 1. If I look on the other side at positive 3, I have again the exact same value there. For my green function, I have the point negative 1, negative 1, which means I should exactly have the point positive 1, negative 1, and we do. All right, and for my blue function, we have a point over here, negative 1, 4. And then on the other side, I have a positive 1, 4. So we can see that reflection again across our y-axis. That's the important thing. We're reflecting across the y-axis. Okay, let's talk about the algebra here. If I plug in a negative x into my x values, I should mathematically get the exact same function. So what I'm going to do is I'm going to plug in a negative x into this, and I'm going to get the exact same function. So let's see what I mean by that. So y equals, instead of x squared, I'll plug in a negative x. So we have negative x squared plus 2. And now if I simplify, again, I get x squared plus 2, which is the exact same function we started with. So now algebraically, I just proved that I had an even function. Okay, let's look at our other function. So we do the same thing. We'll plug in a negative x. So we have negative x squared plus 2 times negative x plus 1. Okay, when I simplify things, we get positive x squared minus 2x plus 1. And as we check things, okay, the x squareds are the same. The negative 2 and the positive 2x, those are not the same, right? So since we don't have the exact same function, this one is not an even function. All terms within our expression have to be exactly the same, otherwise we have not proven that we have an even function. Now our odd functions are symmetric to the origin. That's our diagonal line y equals x, which means for every x in the domain, if we have f of negative x, then we have negative f of x. Okay, that's kind of confusing. So what does that mean? Well, if we had a point xy, then there has to be a point negative x, negative y, the exact opposite. So let's look at an example. Let's say that I had a point, let's say I had the point 2, 3. For this to be an odd function, I would then have to see the point negative 2, negative 3. Let's look at a separate example. Let's say I had negative 3, positive 5. For again, this would be an odd function. I have to have the exact opposite, so I'd have a positive 3 and a negative 5. All right, visually speaking, we're going to be doing two folds here. So for your even function, we just fold it across the y-axis. For an odd function, we're going to fold across the x and the y-axis. So kind of visualize this in your mind. If I were to take this portion and fold it up across the x-axis, then I would have something that looks pretty much like this blue line, right? Okay, now let's take that blue line, and I'm going to take that and I'm going to reflect it across my y-axis. Now, if I had done a better job of sketching this, it would fold exactly onto this portion. So again, just to reiterate, we're going to fold up across the x-axis and then over across the y-axis. For our second function, we do the same thing. I would take this, fold it up across the x-axis, fold it over across the y-axis, and we see it would line up exactly on top of itself, which would prove visually that we have an odd function. All right, algebraically, what we're going to do is we're going to plug in a negative x, and we're going to get the exact opposite. So every term is going to be the exact opposite. Let's look at our first example here. I'm going to plug in a negative x here, so I have g of negative x, which is going to be negative x to the third minus a negative x. Okay, before we simplify this, let's look at what we think we should get. We have a positive x cubed, which means we should get a negative x cubed. We have a negative x, so we should get a positive x. All right, let's go ahead and look at that. If I simplify negative x cubed, I do get a negative x cubed. And then minus a negative x is a positive x. So now when referring these back, we see that we have exactly the opposite. So we have an odd function. All right, second quiz time. I want you guys to go ahead and determine if you think our second function is odd. It's a yes or no question. So go ahead and answer the question and we'll see if you're correct. All right, let's go ahead and plug in some negative x's here. All right, so we get negative x cubed minus negative x squared minus a negative x. What we really would like to see for this to be odd is a negative x cubed, a positive x squared, and a positive x. When I simplify this, we do get that negative x cubed, but minus the negative x squared is going to be still minus x squared, right? We get positive x squared from squaring the negative x, but we are subtracting that, so we still have that negative there. And then for my last term, we do get a plus x, but our x squares did not change, they stayed the same, so we do not have an odd function. All right, that's going to conclude our notes for this section. Go ahead and start working on the homework. Good luck.